Hello and welcome back. Okay, this is the second of two videos adding hardware support for the SPI protocol to our system. In the first video, I identified 4 areas we could work on and handled 2 of them, plus a bit of clock inversion. We handled the chip select with a 138 demultiplexer, and we added a shift register to assist with pulling data in from the external SPI device. In this video, I want to finish off looking at the clock and also look at adding a different shift register for providing the serialization of data going out. Initially, however, we do need to look at adding some functionality to the CPU instruction set to help support what we're doing. So let's take a look at that. So we've got a similar problem here. We've got the MOSI line. We have 8 bits of data on the CPU and we need to shift that out 1 bit at a time. We can solve that in a very similar way with another shift register. But we've got a problem. We need to be able to output 8 bits to do that. And I think for that, we're going to need to make some changes to the actual interface to our SPI circuit. We have a register for GPIO, and I think we need to accept the fact that this is now SPI, and we actually want to separate out SPI data and SPI control as we did for the UART. Now we do need an extra line for that, and the bits on the current output register, that's the control. So that's write only. So let's take device 12 write and call device 14 SPI data. So we're going to have some changes to the main instruction set now. So our current GPIO lines become SPI data, and we're going to need to output SPI control. So we've got 1 unused opcode there. And of course, all of our code's going to have to change here. So we haven't updated this function yet. But of course, this code is a lot closer to the RTC read code as well. That's the code updated. Of course, we've got an additional problem where our pipeline ROMs are not going to be correct. So the current in and out of GPIO pretty much just replaced with the SPI data. So assert IO GPIO becomes SPI data. Load GPIO becomes load SPI data. And interestingly enough, in the header file here, we've defined load 12 as load UART control, but we don't use it anywhere. And of course, we've recycled that as SPI control. Right, if we run this, it should tell me which ROMs have changed. And it's just pipeline stage 2A, which shouldn't actually surprise us because that's the one that controls the assert and load lines from the main bus. Okay, it's been ages since I've had to write a ROM chip for this system. Let's power it back up. And I'm not expecting this to work because we're never actually writing to the control lines here. So now on device 12 write line, I'll move this along. Need to shorten that wire. Let's just take it there. And now we're back to working. Excellent. So now we come on to the output line, and it should be pretty obvious what we're going to do here. We used a shift register to pull data in, and there is such a thing as a parallel to serial shift register that we can use to shift data out. And I'm going to use the 74LS165. Now as a serial input here, I'm going to pull that up for now, but I've got an idea on what to do with that later. A clock inhibit and a clock line. Now we're going to want to invert this relative to the clock we're getting over here. So once again we'll turn an exclusive OR gate into an inverter by forcing one of the inputs high. Shift load. Now this is actively loading while the line is low. So we should be able to just use the load line, which is the register we've assigned to SPI write. There's the serial out. It's just the data lines now, which are going to come from the main bus. So at the top we've got least significant bit on the right. But on the bottom of this chip, the order is the opposite. So we've got an output there. Now I think what I'm going to do is shadow the output we're generating with the bit shifting in code, because I want to confirm that we're getting the same result. Let's go and have a look at the code. Right, so our second output has to pass a non-zero value in. We're outputting it here. Right, let's give that a go. Okay, I'm going to put the yellow trace onto the current data out. So we've left the shifting code in place so we can compare it. And purple trace I'm putting to the output for the shift register. Let's give that a go. And that's not working. So yellow is what I would expect. And the purple's staying 0. Right, let's check the load line. Okay, it's going low roughly where I would expect it. Clock line. Okay, that was a little bit unstable there. Bad connection on the scope probe. Okay, clock's what I would expect though. Right, I want to check that we're actually getting the data right. This bus tester has a load line and I'm getting a 1 there, which is what I expected, and that's consistent with what we're actually seeing on the output. And I think I see it. So this clock inhibit line, I've used a black wire because I want to pull it down, but I've put it into the 5-volt line. Right, so that goes high before we want it to. Also stays high, but then the shift in, we pulled that high, so let's pull it low. So that looks like it's happening a cycle early. Right, let's check the code. Now we invert the clock going into the parallel to serial shift register. Put the data in here. 165 shifts out on a low to high transition, but we're inverting it. So we're looking for a low to high transition on clock. The invert's irrelevant here because we're getting the raw clock signal, not the one going to the device. Okay, so that grabs the next bit we need out, and that gets written out there. but at the same point, we're getting the high to low transition. So that data is going to sit there on the output. Okay, we need to reorder this, but I don't particularly want to break the existing code logic. So let's kind of hack around it. This is going to clear the clock. The rest of the code assumes that's the way it is. Right, so this is very hacky because I need to reorder the code to actually work like this properly, but that will stop the two ways of doing this cohabiting. So I'm going to bring the clock down early. So then when we output this, that first bit is in the output. So it does mean the first time we get to this code, that is redundant. That looks good. So presumably now, if we disconnect the data out and take it from the shift register, this function will continue working. In this code for the read all, I know I'm writing a 0, so I optimized already by not actually bothering to set anything. So I don't need to mess with that at all. We've already fixed this one up, and this is where it gets a bit more interesting. Don't need that anymore, which is the primary speed improvement we're going to see. I think I broke this code at one point. Right, if we swap these around and do that first. We expect A to contain a cleared clock signal. So that loop will work. This now finishes with a clear clock. We'll pop directly into A so we can set it to the output register. Don't need this anymore. Right, so I need to go through and pass over this code to clean up these extra immediate loads I've added, but the loops are what I'm worried about. I believe that's right. More importantly, now I've got a bit of extra control over what's going on, I can probably break these dedicated functions down into some slightly more generic code, but I won't do that now. So at this point, we're going to cause the same problem we saw before, because we're clearing the clock line, which is inverted, which means we're pulling in an extra bit. But interestingly enough, that is not a transition the first time we're into the loop, so this will work as is. But we do need to restore that. So we write the command, then we write the address. Don't need any of that shifting anymore. I'm going to duplicate the output there just because it's going to make it a lot easier to get this code working. Right, so once again, that's safe because we're outputting a low clock line twice with the data in between. That in and of itself could be optimized, but we'll come back to that later. Now, the last time it gets to this point, it's clearing the clock, which is shifting in a different bit. So And then with the write operation, we're just doing the same again with the data. I think we've updated that. Right, so in all of these instances now, our core loop is just toggling the clock line, and that takes us 4 cycles. So 4 clocks per bit of data. Obviously in this version, we've got the loop instructions as well, but down here we've unrolled that, and so it just takes us 4 times 8 in order to achieve the full byte. So the big question has to be, can we do that quicker? We could mess around with the output instructions here, give a second out that lets us just chain 2 out instructions that toggled the clock, and that would double the speed. But a better way of doing this would be if we could just work out some way of connecting the system clock to the output while this was going on. So my thinking here is to modify the clock output circuit to allow for the automatic generation of the clock signal, and then while the data is shifting out or shifting in, we can actually get on with different work. So I'm going to try doing that with a multiplexer chip. The 253 is what I used for the bitwise logic in the ALU. Right, so we've got 2 selection lines, 4 input lines and an output line. Let's get these control inputs low. Okay, I did not pick the most convenient space for this chip. So what I'm going to do is take the lowest 2 bits of our control register and drive the selection lines. So now the output will be whatever is selected from the input based on that selection index. Here's what I'm thinking. Position 0, if both lines are low, I'm going to set low. And then position 1, I'm going to set high. So if those 2 bits are 0, we get a low clock. If it's 1, we get a high clock, which would allow us to continue to treat that bottom line as if it was the bit bang clock line. But I'm going to take the clock off the CPU and put it into the 3rd line. So if I output 0, it's low, 1, it's high, 2, I'm outputting the system clock. These are all off by 1. Right. Let's just have a quick look again at the clock we currently generate. Let's have a quick look at what we get off the system. Well, you can see that's many times faster. Right, so we take that output line and our clock comes from there instead. And this is all going to break. Right, so we don't really have that clock line anymore. Though insofar as it exists, it's there. That's interesting. I had a register name of SPI data and a data definition of SPI data, and it just ignored the clash. Now that was the right thing for it to do, so the code worked, but it would probably be worth me fixing the assembler to error if I ever do that again. That would have been an easy mistake to make. Now, everywhere we currently specify clock, if we replace that with clock high, it will continue to work. Okay, that's not working. Let's see if we can debug that. Oddly enough, we never fixed that up properly. Okay, so now let's see what we can do about this code with the clock control system we have in place now. Okay, so this code is going to end up being an awful lot different now. So if we set clock to auto, it's going to pulse out the main clock. And we want to return it to low. Now, between auto and low, we've got 3 cycles. So it'll take 5 to finish off 8 bits. Then we do that again, and that should be our byte returned. Can it be that simple? I don't think we're handling the first bit right there, but I want to compile and test it. Okay, I want to have a look at the data that's coming back. It's going to be easiest to grab there. No, that's the data that we're sending. That's data that's coming back. So that looks like the last bit is getting stretched. Now, so whatever cycle it's running through should repeat every 60 seconds. Actually, I've got a great idea. Let's simplify this a bit. So this code is reading the seconds in and outputting it constantly. So I'm going to watch this for a whole minute while it loops itself back round. So actually, top bit is set, and then these seem to be changing every other second. So that implies we're reading 1 too few bits in. Looking at the diagram for mode 1, I think we want the clock to go high. And then we output our data. That feels right, actually. We've got kind of a half cycle before starting the main loop. I feel the need to wait on this, but that looks like it's working. And that is absolutely fantastic. The difference between the clocks here is just a single point. So save an extra cycle there. And of course, we don't actually need to separate this out at all because the clock is already running. Now look at that on the scope. That is absolutely awesome. We have a little bit of a preamble there, but once we're into the main data operations, we're running it at the full clock rate. So just to be sure we're working okay, let's try and adapt one of the MCP functions. Okay, so I missed the coding on there as well, but I've just been adapting the MCP write function. It's actually very simple. Once again, we've got the replication of this inner loop, which transfers 1 byte of data. And the code flow is logically the same as it was before, but we take the write command, we generate 8 clock cycles, we output the address command, we generate the 8 clock cycles, and then we output the data and generate the 8 clock cycles. Finish up. It's phenomenally simple code. Of course, this is mode 0. We don't have the extra little half cycle at the start. Okay, well that's not working. See, the scope's getting a bit tough to see, so let's try upper 4 bits. Okay, well I can see a bit of a problem there immediately. Seem to be outputting more than we need. Actually, I don't think we're outputting more than we need. I think it's getting confused about where the signal starts, so I'm guessing I've messed up the chip select. Bingo. Okay, so that's exactly the expected output. Let's restore the original code. And that is working brilliantly. Awesome. Feel a little bit bad leaving anything part done. So let's go and look at read all. This is where it gets interesting. So this reads 8 bytes of data in sequence. So that's pulling in the time and the date. Now I'm just going to grab all of that and trash this. So destination is set to the data. Resetting that because we know we need an address of 0. Invert the clock, clock low, clock high. Yeah, doesn't matter, that's already set. We're shifting out zeros. So, so 8 cycles and the address is shifted out. Eight more cycles and the first byte will be returned. I can read that byte in and save it. That's 3 cycles. So we need to wait 5 cycles and then the second byte is ready. 3rd, 4th, 5th, 6th, 7, 8. Now we could actually do this with a loop because we've got 5 cycles, but let's just paste the code out for simplicity's sake here. This is actually going to start reading bits in from the next register, but that doesn't matter. Let's test that. Right, it's not worked. I think we got an off by 1 error. So that makes logical sense. This is going to take a cycle, so we don't want to wait 16 cycles. We want to wait 15. Bingo. Ah, that is so awesome. And of course the jump in the time is giving you a clue that this is a different day. Okay, I am incredibly happy that we've got that working in the end. So we've taken a fairly simple bit-banged SPI interface and we've taken it with the addition of 3 chips and swapping 2 other chips to something that can transfer data 1 bit per CPU cycle. So at 4 megahertz, that's 4 megabits per second or half a megabyte. And of course, the 2 devices we've got in there on the SPI bus at the moment, they don't really need that kind of data rate, but in the next video, I would like to introduce a device that can productively consume or deliver data at that kind of rate. And that's going to start giving us some functionality in the system that is really interesting. As always, I'd like to thank all my patrons. I really appreciate the support. And for everyone, I really hope you enjoyed this. I'll see you again soon. Goodbye.